You all welcome to workshop technology subject. The last class I gave introduction to this subject. The workshop, the place where some mechanical task is carried out, we can call it as a workshop. So what are the activities done on the workshop? It may be a manufacturing, repairing or maintenance work. Then I gave introduction to the operations, some operations of the workshop operations. Then we identified the metal cutting is the main operation done on the most of the workshops. So then first I defined the metal cutting operation. Metal cutting is a material removal process using the cutting tool to obtain the required geometries and dimensions. In this process, this process is depend on the lot of parameters that mean the output from the process depend on the input parameters. So in last lecture I gave introduction to these input parameters and output parameters, how this output is depend on the input parameters. Then you should be able to select the proper input parameter to get the required output. Okay, so you should have to select the proper input parameter, you should have practical knowledge and also the theoretical knowledge. Okay, today also we are continuing with this topic. Okay, before going to the theory of the today's theory, so I am going to introduce some videos on machine operations. Okay, let's see these videos, then let's move to the theory of the today's class. Lawan. Boleh. Jadi. Jadi biar nanti. මේක තුනක් වෙනවනේ. ඔව්. මේක තුනක් වෙන ඔන්න පිළිවෙලට තමයි දාන්නේ.
කියන්නේ කියනවා.
එකක් දාලා බෙන්නවා ඇති.
හා?
එකක්
ඉස්සරහට භාගයක්
Okay, then next subtopic is classification of metal cutting. The classification of metal cutting. All the metal cutting operation we can classify into two, called orthogonal cutting and oblique cutting. Okay, this is called orthogonal cutting. Oblique cutting. Orthogonal cutting and oblique cutting. This one also called 2D cutting, two-dimensional cutting. Later I will explain why this name is given. This is called 3D cutting. 3D cutting. Okay. Then the property of this oblique cutting and the, let's see what are the properties of this oblique cutting and the orthogonal cutting. In orthogonal cutting, cutting edge is perpendicular to the direction of cutting. Okay, in orthogonal cutting, cutting edge is orthogonal to the direction of cutting. Okay, let's take this kind of a workpiece. Here the removing chip in the metal cutting operation. Okay, then let's take the cutter. Let's take this is the cutter. This is the cutting tool. Okay, the cutting tool. Okay, then the workpiece. Okay, this is the workpiece. This is the cutting tool. Cutting tool. You can see this the direction of cutting. This is the direction of cutting. This is the direction of cutting. This is the cutting edge. This the direction of cutting. Then this is called cutting edge. You can see the cutting edge at an angle perpendicular to the direction of cutting in orthogonal cutting operation. Cutting edge is perpendicular to the direction of cutting. Now let's see oblique cutting operation at an angle to the direction of cutting. Cutting edge at an angle to the direction of cutting. Okay. The cutting tool. Cutting tool. And this is the workpiece. The workpiece. Okay. In this situation, you can see this is the cutting edge. Then this is the direction of cutting. Direction of cutting. You can see this cutting edge at an angle to the direction. If we draw the perpendicular to the cutting edge, you can see, and the direction of cutting, you can see there's a inclined angle. This I called oblique angle. Oblique angle. Okay. So the orthogonal cutting, oblique cutting. So what is the difference between these two? In orthogonal cutting, cutting edge at an angle perpendicular to the direction of cutting. This is the direction of cutting, this is the cutting edge. You can see this is perpendicular. Then oblique cutting operation, cutting edge at an angle to the direction. Here this is the direction of cutting. Here you can see this is at an angle to the direction of cutting. Okay. Then this inclination, this angle is called oblique angle. So in this situation, removing chips form the coil shape. It forms the coil shape, but in here it forms the curl shaped chip. Okay. When increasing the I value, I, then I dash. When increasing the I value, the curl shape, the pitch value increases. This pitch value increases. For I dash is greater than I. Okay. Then any metal cutting operation we can categorize under these two. Okay. Oblique cutting and orthogonal cutting operation. Both are used in industry for metal cutting operation in different situations. In orthogonal metal cutting operation, you can the properties of orthogonal metal cutting operation. All the force vectors acting on a cutting tool, acting on a workpiece, we can represent on a two-dimensional plane. Okay, vectors we can represent on a two-dimensional plane, and also the velocity vectors, the cutting velocity, chip velocity, and also the shearing velocity, we can represent these velocity vectors. We can represent on a two-dimensional plane. Okay, but if you are going to the oblique cutting operation, the velocity vectors and also the force vectors are in three-dimensional space. So those we can't represent in a two-dimensional plane. Instead, we have to use three-dimensional space vectors to represent these forces and the velocities. Okay. Basically, we can say this analysis of oblique cutting operation is difficult because three-dimensional vector analysis is knowledge about the three-dimensional vector analysis is needed to analyze the oblique cutting operation. But in simply we can analyze the orthogonal cutting operation, because in a planar vectors we can easily calculate, we can do these calculation easily with the planar vectors. Then another important thing is all the force vectors are acting on the two-dimensional plane. When mounting a workpiece, yeah, it is enough to give two-direction fixtures. But in this situation, we have to consider the fixtures in three dimensions. In three dimensions, we have to consider when giving support for when mounting the workpiece on a table of the machine tool. But in this situation, it is enough to give the two-dimensional plane support for when mounting the workpiece on a machine tool table. Okay. Then another disadvantage in orthogonal cutting operation is, you can see in orthogonal cutting operation, let's take this is the workpiece, then this is the cutting tool. This is the cutting tool. When engaging this cutting tool with the workpiece, it produces the impact force. It suddenly engages in a larger length, over this length. But in here you can see, so I will draw the two-dimensional diagram for this one. Yeah, I will draw two-dimensional diagram. Let's take, this is the view looking from the top. This is for the orthogonal cutting. Then this is for the oblique cutting. Okay, this is for the oblique cutting edge at an angle to the direction of cutting. This is the direction of cutting in both situations. This is oblique cutting. Okay. Then you can see in orthogonal cutting operation, it suddenly engages along this length to the workpiece. The tool is suddenly engaged along this length to the workpiece. But in here, it is when engaging the cutting tool to the workpiece, it is very smooth engaging. It engages from the small length area, then it is gradually developed, gradually enters to the workpiece, not suddenly engage. So that it having the smooth engagement, because of it having the smooth engagement, that tool edge having the higher safety. Higher safety mean the tool wear is less, because of in this situation it produces the impact force on the workpiece, so it causes to blunt the tool tip. Okay, but the tool life is more. Here tool life is less. Okay, tool life is less. And also another important thing is, you can notice the metal cutting operation is limited in orthogonal cutting operation to a small area, but in oblique cutting operation it is spread to a wide length of the cutting edge. So that metal cutting operation done in a wide length of the cutting tool edge, but here it is limited to a small length. So that means all the forces, all the thermal, all the heat generation also limited to this small area. So it causes to wear out this small area immediately. But when it distributed to a longer length, the pressure acting on the cutting tool is reduces, and also the thermal distribution is higher, so it has the lesser tool wear comparing to orthogonal cutting operation. These are the advantages, disadvantage in oblique cutting and orthogonal cutting. As the advantage in orthogonal cutting, we can easily analyze the orthogonal cutting, because in all the force vectors and the velocity vectors we can represent on a two-dimensional plane, we can easily analyze and optimize. But when going to oblique cutting, it is difficult to analyze because three-dimensional vector analysis is needed. It's difficult to optimize the oblique cutting operation also. And also another advantage, the simple support is enough when mounting the workpiece on a machine tool table. But in this situation, we have to consider three different direction support when giving when mounting the workpiece on a machine tool table. These are the advantage and disadvantages in oblique cutting and orthogonal cutting operation. Okay, then various operations having the orthogonal cutting with the orthogonal cutting and oblique cutting, you will experience. Try to identify this orthogonal cutting operation and oblique cutting operation when you are doing the workshop practical classes. You will experience both the cutting operation in your workshop practical classes. Okay. Okay. Now you know the classification of metal cutting operation, orthogonal cutting, and oblique cutting operation. Under this first year level, we are in detail discussing about the orthogonal cutting operation. We are mainly focusing to the orthogonal cutting operation. In second year, third year level, those who are doing the mechanical engineering subjects, you will learn oblique cutting operation and oblique cutting operations in detail. Okay, the orthogonal metal cutting operation. Orthogonal metal cutting operations. In any orthogonal metal cutting operation, we can draw this kind of two-dimensional diagram representing a workpiece, cutting tool, and the removing chip. Okay, this is the removing chip. This is the workpiece. Okay, this is the workpiece. This is the removing chip. The materials are removed by the form of chips, small strips. Okay, in the metal cutting operation, the materials are removed by the form of chips. These are chips, metal strips. So then this is the cutting tool. Cutting tool. Okay, chip, cutting tool, and the workpiece. Okay, then this is called let's take this is a clamp on a machine tool table. The tool is moving in this direction with the cutting speed. Okay, then I'm going to introduce another important parameter, rake angle. Let's take this is the expected finish surface. This is called finish surface. Okay, this is called expected finish surface after machining. Okay, then this is the tool edge. Then I'm going to draw the perpendicular to the expected finish surface at the cutting edge. This is the perpendicular. Okay, then top of this cutting tool is called tool face. Okay, tool face. Then the bottom surface of the tool is called tool flank. Tool flank. Okay, then angle between these two, tool face and this drew perpendicular line called alpha. Alpha is a very important parameter in metal cutting operation. Alpha rake angle. Alpha rake angle. Okay, very important parameter. Okay, the metal cutting operation we have to essentially set this alpha rake angle value depending on the work we are doing, depending on the cutting tool material, depending on the workpiece material, and also the type of cut we are doing. We have to set suitable alpha rake angle value. Okay, in some situation negative alpha values also using when machining, especially when machining the very hard material. Negative rake angles also using. So negative rake angle, what is the negative rake angle? Okay, negative rake angle. Negative rake angle mean the cutting tool, okay, the workpiece, the removing chip. Okay, in this situation you can see the perpendicular to the finished surface, the other one. Then this is the tool face, no? Tool face. You can see this angle is negative alpha. Okay, when machining the, especially when machining very hard material, negative rake angles are using. Okay, later you are learning this selecting alpha value for certain machine operations we are discussing. Okay, then in this level try to identify this component. Then this is called undeformed chip thickness. For this orthogonal cutting operation, it is equal to d, depth of cut. Okay, depth of cut d. Then this is called t, chip thickness. Chip thickness. Okay, then this is called clearance angle. Let's take theta. Okay, the angle between the finished surface and the tool flank is called clearance angle. Okay, then this is, let's take this beta, the tool angle. Okay, okay, for any orthogonal metal cutting operation we can draw representing these parameters, we can draw this kind of diagram. Okay, the cutting tool, workpiece, removing chip, then the undeformed chip thickness, clearance angle, rake angle, we can represent. Okay, then another important parameter, chip thickness ratio. Okay, chip thickness ratio, R d divided by t is called chip thickness ratio. Chip thickness ratio. Okay, then in this diagram we have to identify these two zones. Okay, here you can see this zone is called primary shearing zone. I will put the number one is called primary shearing zone, number 2 is called secondary shearing zone. Here this is the number 2. Okay, primary shearing zone and the secondary shearing. Identify these two shearing zones. I will explain. What is the shearing? The word shearing. First, let's define the shearing. What is the shearing? The word shearing. The shearing means slipping the material plane parallel to each other. slipping the material plane planes parallel to each other. That is called shearing. Okay. For example, if take the certain material, this is let's take this is the material. Then in this direction the force is acting. In this direction another force is acting. Okay. If you take the middle plane, you can see this top part tends to shift on this bottom part along this line. Okay, tends to. When it reaches to a certain force value, it actually slips, called shear failure. Called the shear failure. That means it shift forming this kind of deformations. Okay. You can see this due to application of this force, there's a slipping in between these two planes. Let's take the plane belongs to the bottom surface and the planes belongs to the top surface. There's a relative motion in between these two planes, parallel planes inside the material. This is called the shearing effect. Okay, shearing effect. Okay. Here also the same as in this example, we can separate the two planes at here. This is the plane belongs to the chip. This is the plane belongs to the workpiece. Okay. Due to the force applied by the cutting tool, this chip tends to move on this plane called the shearing. Okay. This chip tends to move, slide on this plane. So I will enlarge and draw that one. Okay. This is the workpiece. This is the workpiece. Then this is the chip. If we separate these two planes in this way, we can have this kind of diagram. Okay. Due to the force acting on it, this plane slip on this plane. This is stable. You can see this plane is slip. If you separate these two planes at the mating surface, you can see this plane is slip on this slide on this surface. Okay, called the shearing. Then this is called the primary shearing zone. Okay, primary shearing zone. It's a heat generating zone because of the shearing friction. There's a huge friction in between resisting this slipping action. Okay, so produce when it the huge work have to act on this chip against this resisting force. So it is a very high heat generating action. So this is called primary heat generating zone. This zone also called primary shearing zone, also called primary heat generating zone, because of the shearing friction, higher heat is generating around in this region. Okay. Then secondary heat generating zone. Secondary heat generating zone, that means a secondary shearing zone, there's a rubbing action in between removing chip and the surface of the cutting tool. Okay. But in this situation there's no the two surfaces are rubbing each other, not inside the same material. This is the cutting tool. This is the cutting tool. Okay. The very high pressure acting on this mating surfaces, the bottom surface of the chip and the cutting tool tool face, very high pressure is acting. Okay. And also the width relative to the cutting tool, this chip flows along this direction. Okay. Because of this friction in between these two surfaces, very high heat is generated. Heat is generated, so that the temperature increases in this region because of the generation of heat. Okay, this region also called secondary heat generating zone. Okay, secondary heat generating zone, that heat generated in this region is less than heat generated in this region normal situations. Okay, this is also called secondary heat generating zone. This region is called primary heat generating zone. Primary heat generating zone. Okay, the both are heat generating zone. So in metal cutting operation, because of this heat generation, the temperature in this region increases. Okay, some situation it reaches to the melting point of the workpiece material. Okay, that is why the built-up edge is generating in metal cutting operation. Okay, so that to reduce the temperature, the coolants are applied. Normally, the two type of coolants using the oil-based coolant and the water-based coolant. Okay, normally the two nozzles are using targeting the two heat generating zone, the primary heat generating zone and the secondary heat generating zone. The carbon tetrachloride is the chemical included in this cutting fluids. The oil-based coolant and the water-based coolants are applied. Okay. Okay, then I think you all clear with this diagram and these parameters, how we can represent in orthogonal metal cutting operation: rake angle, clearance angle, tool nose angle, and the undeformed chip thickness, and also the primary heat generating zone, secondary heat generating zone, and how the coolants are applied, and also the definition of the shearing, and also the negative rake angle. I think you all clear with this thing. Okay. We discussed about the primary heat generating zone and the secondary heat generating zone, about the this is the removing chip, then this is the workpiece. I will draw the cutting tool also. This is called the cutting tool. Workpiece. This tool is moving in this direction with the velocity v. Okay. Let's take the workpiece is clamped on this machine tool table. Okay, then last lecture we identified this zone as the primary heat generating zone. Primary heat generating zone. Okay, then this is called secondary heat generating zone. So the primary heat generating zone, because heat is generated due to the shearing friction. The secondary heat generating zone, the heat generated due to the rubbing action in between the removing chip bottom surface and the tool face. Okay, so today I am going to discuss first thing, built-up edge. Built-up edge. buildup edge. Then in metal cutting operation, the buildup edge should avoid in all the metal cutting operation. We are calling the BUE. The BUE built-up edge should avoid in all the metal cutting operations. What is meant by the built-up edge? You can see because of heat generation in these two regions, the temperature in this region increases. Okay, temperature in this region increases. Then the heat also accumulate in this region. This region, the temperature increases. When it reaches, in some situation, it reaches to a melting point of the work material. It reaches to a melting point of work material, work piece material. Okay, so then what happened? Because of the mortar metal and also the very high pressure in between this acting on this tool, the material in this region molten. Okay, and adheres to tool tip. So I will draw the tool separately. Okay, the material closer to this tool tip molten and adheres to the welded to tool tip. Okay, then because of this welding nugget, tool tip become blunt. Okay, the cutting with blunt tool tip also accelerate heat generation. Cutting with blunt tool tip also accelerate heat generation. So that what happen? The rate of temperature increase also increases. So what happen? The more metal molten and more metal deposit on this cutting tool. So what happened? This is called newly generated cutting edge called the built-up edge. BUE. Okay, BUE. This newly generated cutting edge called the built-up edge gradually develop with the time. Gradually develop. So in that situation, what can you say about the force acting on the cutting tool? Because of this huge blunt tool tip, the force acting on the cutting tool also increases because of this blunt tool tip. Okay, when it reaches to a break-in limit of the cutting tool, what happens? Tool fails. Tool may bend or fracture. Fracture may occur. Okay, this is called the built-up edge generation in metal cutting operation. In any metal cutting operation, the built-up edge should avoid. So, what are the methods to avoid the built-up edge? Okay, what are the methods to avoid the built-up edge? The first thing, the selection of proper cutting tool parameters. Okay, we have to select suitable cutting velocity, depth of cut, rake angle values, alpha values for certain to avoid built-up edge. By selecting the suitable cutting parameters, in last lecture we discussed there's a several number of parameters. This operation output is dependent on the several parameters. By controlling these parameters, we can control the we can avoid the generation of built-up edge. We can avoid the generation of built-up edge. Okay, then we can avoid the generation of built-up edge. Then another important thing is if you can apply the coolant. The coolant also very important to avoid the built-up edge. When applying the coolant, we have to consider effective use of coolant. Effective use of coolant means the coolant have to effectively apply on the targeting two heat generating zone. Okay, effective use of coolant, also an important thing, important to avoid the generation of built-up edge. Okay, so what are the two methods to avoid the built-up edge? Selecting the proper input parameter for the metal cutting operation and applying coolant to the coolant in metal cutting operation. We can avoid the generation of built-up edge. So what is the disadvantage in generation of built-up edge? It causes to fracture the tool failure, and also it produces the poor surface finish in metal cutting operation, because the tool tip become blunt. It produces the poor surface finish, and also the metal deposit in the finished surface also produce on the because of the built-up edge. So generation of built-up edge we can identify by looking closely observing this removing chip. Okay, by closely observing this removing chip, you can identify the metal deposit in the bottom surface of the removing chip. In that way, we can identify the built-up edge is going to develop. Okay, we have to get the quick action to avoid. In that situation, we have to get the quick action to avoid the development of the built-up edge. Okay. Then let's move to some calculations regarding to this two-dimensional metal cutting operation. The last class we discussed this two-dimensional metal cutting operation means the orthogonal metal cutting operation. Okay. Calculations regarding to two-dimensional metal cutting operations. Calculations in 2D metal cutting. I will draw the diagram for the two-dimensional metal cutting operation. First we are going to obtain the equation for the 5. What is 5? Yeah, the 5 I will explain what is meant by the 5. Okay, this is the diagram for the this kind of diagram we can draw for the two-dimensional metal cutting operation. This is the workpiece. Then the cutting tool. Cutting tool. Then this is called shearing plane. Okay. This is called shearing plane. So angle between the expected finish surface and the shear plane, this angle is called 5 shear plane angle. Okay, shear plane angle. Then this shear plane angle we can't measure using the instrument because it is inside the material. You can see it is inside the material. Okay, we can't measure, but we can mathematically determine this shear plane angle if we know the these things: the undeformed chip thickness T1 and the chip thickness T2 and the rake angle alpha. We can determine the 5. We can obtain the equations. These things we can measure. The T1 we can measure, T2 also we can measure, alpha also we can measure. These are measurable data. Using this measurable data, we are going to determine this unknown 5. Okay. So considering this geometry of this figure, we are going to obtain the equations for the 5. Okay. Then let me obtain this equation A B. Okay. Then in last class I gave R. What is R? R mean R is equal T1 divided by T2 is called R, called the chip thickness ratio. Chip thickness ratio. Okay. Chip thickness ratio. Okay. Then we can write the, considering the geometry of this figure, we can write the two equations. We can write the two equations. T1 is equal AB sine phi. Okay. Then I will draw the geometric construction for this one also. The perpendicular to this surface from this B point. Okay. Then what is this angle? This angle. This angle. Here this angle is alpha. Alpha plus. Then what is this angle? This is 90 degree. 90 minus 5. Okay. This angle. So we can write 90 minus 5 minus alpha for this angle. Okay. 90 minus 5 minus alpha. Okay, then from this triangle, so this is the point. Let's take the C point, this point. From ABC triangle, I can write here, this is the T2, no? The BC is equal T2. BC is equal T2. Then AB sine 90 minus 5 minus alpha is equal T2. Okay, is equal T2. Let's take this is equation 1, this is equation 2. Okay, so I'm going to divide the equation 1 by equation 2. Okay, I'm going to divide equation 1 by 2. Then I'm getting T1 divided by T2 is equal AB sine 5 divided by AB sine 90 minus 5 minus alpha. Okay. The further we can simplify T for the T1 divided by T2, we can put the R, called the chip thickness ratio. Okay. So the AB we can cut sine 5 divided by sine 90 minus 5 minus alpha. It means the cos 5 minus alpha. So I am going to expand this this one. Cos 5 minus alpha. R is equal sine 5 cos 5 cos alpha plus sine 5 sin alpha. Okay, sin 5 sin. Then both the numerator and denominator I am going to divide up by the cos 5. Okay, both the numerator and denominator I am going to divide up by the cos 5. Then R is equal, then by dividing the cos 5 we are having tan 5. Okay, cos alpha plus tan 5 sin alpha. Okay, by making by taking the cos alpha plus r tan phi sin alpha is equal tan phi. Okay. Then by taking this 5 terms into one side, I'm going to take r cos alpha is equal 1 minus r sin alpha into tan phi. So by making the tan phi into subject, tan phi is equal r cos alpha divided by 1 minus r sin alpha. So then by making the phi into subject, tan inverse r cos alpha divided by 1 minus r sin alpha. This is the equation we can use to determine the phi. Okay, this is the equation we can determine to phi. So then r is a known value. We can measure actually the t1 and t2 we can measure. Alpha also we can determine. Okay, then using these measurable values alpha and r, we can determine this unknown value phi. This phi is important in further calculations. This is the basic calculation, first calculation in two-dimensional metal cutting operations. Okay, when we are going to determine this r value, okay, r mean t1 divided by t2. Then it is very difficult to measure accurately these t1 and t2. Those are very small values. So then taking the ratio of this small value also giving the higher error. So that there's a method to determine this r value in accurate manner. Let's take this is the workpiece. Then this layer we are going to remove using the cutting tool edge. Okay, this kind of layer we are going to remove using the cutting tool edge. Then the length of this layer, let's take it as L1 before it remove from the surface. Then let's take this thickness as T1 before it remove. Okay. Then what happens after it removes? Its original thickness vary. So let's take it forms this kind of coil shape. Okay, let's take it form this kind of coil shape. Then in this situation its thickness T2, then its length, this curved length, let's take it as L2. Okay, curved length L2. We are assuming in a deformation perpendicular to this surface is 0, so that the volume of these two should equal before it remove from the work surface. After it remove from the work surface, the volume should be equal, so that the T1 into L1 in the perpendicular to the surface, the dimension, let's take it as W. Then this volume of this one L2, T2, the perpendicular to this surface, dimension is W. That is not vary in metal cutting. We are assuming that is not vary. Okay, because it is a two-dimensional metal cutting operation, the W2 is not vary. Then we can further simplify this one by taking the T1 divided by T2 is equal T1 divided by T2 is equal L2 divided by L1. L2 divided by L1. The T1 divided by T2 is equal L2 divided by L1. So that means we can what it means that it is equal to the chip thickness ratio. That means chip thickness ratio we can calculate by dividing L2 by L1. So L2 we can easily measure by measuring the length of this removing chip, and L1 also we can easily measure with a greater accuracy. So then R we can determine with the very high accuracy compared to taking these two ratio by taking this length ratio. Okay. Here we discuss how to calculate the shear plane angle in two-dimensional metal cutting operations. Okay. Then let's see the velocity relationship in metal cutting operations. Okay, next subtopic is velocity relationship in metal cutting. In orthogonal metal cutting. Okay. So I will draw the orthogonal metal cutting diagram. This is our workpiece. This is the removing chip. Okay. Then let me draw the cutting tool also. Cutting tool. Okay. This is the workpiece. The removing chip. Okay. The earlier we defined, let's take this is mounted on the machine tool table. Then the cutter is moving with respect to the stable workpiece. Then this velocity is called V cutting velocity. So how we define the cutting velocity? A relative velocity in between the workpiece and the cutting tool edge. Relative velocity in between the cutting tool edge and the okay. For the cutting tool I am using the C. For the workpiece I am using the W. For the chip I am using the C. That means V velocity mean we can represent this V velocity by a vector. It is in this direction. V that means it is called V, the velocity of the I am taking this one as T. Okay, the tool, chip and the workpiece. Okay, the velocity of the tool with respect to the workpiece. This is the, you all familiar with this relative velocity notation. The tool velocity with respect to the workpiece. The T means the cutting tool, W means the workpiece, C means the chip. Okay. Then I will draw the shear plane also. This is the shear plane. This angle is called 5 shear plane angle. Okay. Then you can see the chip. So what is the velocity of the chip with respect to the cutting tool? That means if cutting tool is stable, what is the direction of chip velocity? Okay. If the cutting tool is stable, it means chip moves along this direction. No? That means the chip flows over the face of the tool. That means with respect to the cutting tool, chip flows in this direction over the tool face. That means we can draw the rectangle also in here. This is called alpha rectangle. So what is the direction of the chip with respect to the cutting tool? That is at an angle alpha to the vertical in this direction. So I am using the letter V, chip flowing velocity over the tool face, Vf I am using. Okay. Then is equal to V, the velocity of the chip with respect to the cutting tool. Okay, with respect to the cutting tool. Okay. So I am using the letter subscript letter for the C. You with the cutting speed. Vc means the cutting speed, Vf means the chip flowing velocity, chip velocity with respect to the cutting tool. Okay. Then if you take this chip separately, you can see in the area I explain this one. If you take this chip separate, I am going to separate this chip at the shearing surface, shearing plane. Here this is the workpiece. Okay, this workpiece is stable. That means this surface is stable. Okay, this surface is stable. With respect to the workpiece, what is the direction of movement of the chip? Okay, what is the direction of movement of the chip? That is in this direction, no? That is in this direction. This velocity is called Vs, shearing velocity. Okay, that one also we can represent by a vector. This angle, what is this angle? 5. This velocity vector at an angle 5 to the horizontal, Vs 5 is equal V shearing velocity, V chip velocity with respect to workpiece. Okay, here the Vc means the cutting speed, Vf means the chip flowing velocity, Vs means the shearing velocity. Then these are the vectors, the relative velocity vectors we can represent in this way. Okay. Then in your A level, you know this velocity we can add. This relative velocity we can add using the by drawing the relative velocity triangle. Okay, so I am going to add these relative velocities using the velocity triangle. Okay, then for this one, first I am going to draw the relative velocity diagram for this. Using the relative velocity equation, V T W is equal V T C plus V C W. You can write, you are familiar with this relative velocity equation. In your A level also you are using this equation. Okay. Then what is VTW? That is in this direction. VC is equal VTC, that is in this direction, opposite. VCT is in this direction. That means the velocity of the chip with respect to the tool in this direction. So velocity of the tool with respect to the chip should be downward direction. This angle is alpha plus VCW that is in this direction, 5 Vs Vf. Okay, this is the vector addition. These velocity vectors we can represent in this way. Okay, then using this vector addition, we can represent on a relative velocity triangle. This vector addition we can represent on a relative velocity triangle. Okay, And let's see how to represent it on relative velocity triangle. Okay, then this is the VC is horizontal, VC, the VS VS, this is VF, this angle is 5, this angle is alpha, okay, this angle is alpha. Then we can find these angles. This is 90 minus alpha. Then what is this angle? 180 minus 90 minus alpha minus 5. 90 plus alpha minus 5. 90 minus 5 minus alpha, this angle. Okay, then we can apply the sine rule to relate these velocities. Okay, to this triangle I am going to add the I am going to use the sine rule. Okay, sine rule. Okay, VC divided by sine 90 minus 5 minus alpha is equal VS divided by sine 90 minus alpha is equal VF divided by sine 5. Okay, then make a this one we can further simplify. VC divided by here cos 5 minus alpha is equal VS cos alpha is equal VF sin 5. Okay, VF sin 5. In this equation, the VC is a known value. Then alpha is a known value. The 5, we have an equation to determine the 5, so that means it's a known value. Then the VS and the VF are unknown parameters. Okay, VF and VS are unknown parameters. So I am going to find this unknown parameter using the known parameters. So we can write the VS equation. VS is equal VC cos alpha divided by cos 5 minus alpha. Okay, in the same way we can write the equation for the VF. VF is equal VC sin 5 cos 5 minus alpha. Okay, this is how we can calculate the shearing velocity and the chip flowing velocity in a two-dimensional metal cutting operation. If we know these two values, the V shearing velocity and the chip flowing velocity, we can determine the rate of heat generation in these regions. Okay. Today I am going to enough for today. Then let's continue on next day class. Next day class we are going to discuss the force relationship in metal cutting operations. Okay, thank you.